Whether you're planning to migrate an existing application to microservices or adopt a microservices architecture from the start of a brand new project, there are some very important architectural decisions that you need to make up front. My name's Mark Heath, and in this module, we'll discuss some of the key architectural principles for how we define a microservice and its components. We'll begin by discussing the fact that you don't have to start with microservices. It's possible to evolve an existing application towards them. We'll look in a bit more detail at some of the key definitions of a microservice, including the fact that a microservice should be autonomous, which means it owns its own data. And a microservice should be independently deployable, which means it needs to have a clearly defined and backwards compatible public interface. Finally, we'll discuss the tricky challenge of how we can identify suitable service boundaries for our microservices. We'll look at some guidelines for breaking applications into microservices, including the idea of identifying bounded contexts. It's quite possible that you already have an existing application with a monolithic architecture, or maybe you've even got what we described in the previous module as a distributed monolith, where you've got several services that are tightly coupled together and not independently deployable. The good news is that it's perfectly possible to evolve towards a microservices architecture. You can augment a monolith with microservices, where every time you add a new capability, you create a new microservice. And you can decompose a monolith into microservices, where you identify existing capabilities that should be extracted out into their own independent microservices. In fact, some people argue that you should avoid starting a brand new project with a microservices architecture. The benefits of microservices are not typically seen in small new projects, and it can be very hard to get your service boundaries right. So it might be better to allow a system to grow a bit until it becomes apparent what an appropriate segregation of responsibilities into microservices would be. Now, of course, when you are using microservices, at some point you're going to need to identify the responsibilities of a microservice and define what its public interface should be. So let's look next at some of the key principles of microservices that help us make these sort of decisions. Earlier in this course, we said that microservices are autonomous and independently deployable. And a key part of achieving these goals is ensuring that a microservice owns its own data. In other words, we're not allowed to have this sort of situation where multiple microservices both read or write from the same data store. Instead, each microservice should have its own data store, and any other microservice wishing to access that data needs to do so via the public API of the microservice that owns it. Now, there are some obvious trade-offs here. By splitting our data out, it means that we can no longer perform database joins across the data that's owned by two different microservices. Instead, we're going to have to make separate calls to each database. And we can no longer update two tables owned by different microservices within a single database transaction. Instead, we'd either have to use distributed transactions, which are very complex to implement, or more commonly, design our system to work in what's called an eventually consistent manner, where we may have to wait a while for the overall state of the data to be fully consistent. What this means in practice is that when a single business operation requires updates to more than one data store, there's going to be a short window of time when the change has been made in one data store but not the others. And so you need to develop your application in a way that is able to cope with this temporary inconsistency. Now, there are ways to mitigate these issues. If we define our service boundaries well, we can minimize the need to aggregate data from multiple microservices to perform a single operation. Another approach is that one microservice might hold its own cache of a subset of the data that's owned by another microservice. An example of this might be that rather than having to constantly talk to a user profile service to get the name or email address of a user, we could maintain our own cached copies of this data. And this approach greatly improves performance because it removes the need for lots of chatty network communication, and it improves availability, since now our microservice is able to do its job even when the user profile service is unavailable. It's important that when you're considering how to break your application into microservices, that you identify natural seams in the database schema, and this will help you avoid the performance penalties of having to involve multiple microservices in a single business operation. To illustrate how microservices should own their own data, let's take a look at the eShop on Containers sample application that we introduced in the last module. We can see that the catalog service uses a SQL Server database. The ordering service also uses SQL Server, but it's a different database. Neither of these services can see or access each other's data by going directly to the database. The basket service uses a Redis cache, and this is a more appropriate choice for short-lived data. We can also see that document databases such as Cosmos DB or Mongo have been chosen by some of the other microservices in this application. And so this architecture illustrates two key microservice characteristics. First, each microservice in eShop on Containers owns its own data. And second, each microservice is free to use the most appropriate database technology for the type of data it needs to store. This breakdown of microservices also highlights a way to approach one of the difficulties that we just discussed. The ordering microservice has got a concept of an order item, which represents a single item in your order. The order item entity contains a product ID, a product name, and a unit price. But hang on a minute, shouldn't the catalog microservice be responsible for owning product names and prices? And yes, indeed, the catalog microservice has got an entity called catalog item, which has an ID, a name, and a price. So when you order something, the ordering microservice records not only the ID of the product you ordered, but also takes a copy of its name and price. And so we've actually got duplicate information, which is sometimes referred to as denormalization in databases. Now, this means that if we were to update a product's name or price in the catalog microservice, then the information in the order item would become stale. So wouldn't it be better then if the ordering microservice didn't store the product name and price, and instead asked the catalog microservice whenever it needed it? Well, actually, maybe not. For one thing, that wouldn't perform quite so well, as now we've introduced another network call. But another consideration is that it might actually be a good thing for your order to include the name and the price of the product as it was at the time when you placed the order. In other words, the ordering microservice doesn't really care about what the current price and name of the product are. What it cares about is what they were at the time you placed the order. And so in fact, this isn't really duplicate information. These pieces of data have different meanings within the context of each microservice. And so duplication of data between microservices and the inability to do a direct database join between the data owned by two microservices is not necessarily the problem that it might at first appear to be. The fact that a microservice owns its own data leads us to the realization that a microservice is not necessarily a single process running on a single host. Often, at a minimum, there's your code, perhaps implemented as a web API, and the database. So that's at least two processes, and often they're not running on the same host. If we scale out, now we've got multiple replicas of our code running on different hosts and sharing access to a single database. And if we were to configure our database for replication or sharding, that too might be running on more than one host. Our microservice might also have a cron job working on a schedule to perform some kind of data maintenance. And maybe it has another process that's listening for messages on a queue that trigger various other data updates. So in fact, there may be several different hosts and processes involved in a microservice, but conceptually, together they form a single microservice, and it's only these components that are allowed to access the shared data. We can see this illustrated again in the eShop on Containers sample application. If we look at the ordering service, we can see that it not only contains a web API called ordering.api, but there's a separate process to implement background tasks called ordering.backgroundtasks, which is used to provide a grace period feature. And this is a perfectly acceptable design for a microservice. You're not forced to have all of the microservice code running in a single process. The important thing is that conceptually, a microservice has a clearly defined boundary with a public interface, and its data can only be accessed through that public interface. Let's talk about microservice interfaces next.